All right, how is everyone doing today? Good? All right. Okay. Okay, so our extra credit activities, you can find the one in Achieve. You may have already found it because I opened it up on Friday, is here. So you can either, okay, cool. So some of you have already found it. So it's either under the exams module directly, or if you do that, click here on the midterm and final exams button, you will find the Achieve assignment. Ooh, don't go there. You will find the Achieve assignment listed out, saying that you can use absolutely any resources, including AI, other people, your book, the hints in Achieve. You can use literally anything as long as you understand the material. So whatever helps you is all fair game. It'll be due at 11:59 p.m. Eastern on Thursday, December 5th. That is reading day. So that'll be the extra credit assignment. Up here is also where you will find the link to the Zoom recording for Friday, if you hadn't found that already. It is also under the Carmen Zoom tab. So that's where all of the lecture recordings are found. So if you go Carmen Zoom, Cloud Recordings, they're all listed by date. But I also put a link in here. And then, well, whatever. There was a request to see the annotations. They are a little overwhelming without context. So they exist, but the recording is probably better to look at because that looks like a disaster. But it exists. People asked for it, so there you go. So there are the annotations and the metacognitive activity. The link for that will be available this afternoon. So that'll be the one where you just complete it and you will get full credit for it. In Canvas, I'm having a hard time setting up extra credit. So Achieve, I was able to select the option for extra credit. It'll be interesting to see how Achieve syncs with Canvas and if Canvas recognizes extra credit, because Canvas is kind of struggling on that front. If that's the case, then I will manually input it as extra credit, in which case then it'll have to be an assignment out of 0, and then I will just go in and actually give you like the 10 out of 0 or 20 or whatever you earned. I'll have to manually input it for each of these assignments. But I'm trying to set it up so it's just, directly extra credit to make it a little bit easier so that as soon as it's done, you immediately see your grade, is the hope that you'll see it boosted. Yeah. Yes, it's getting added to the midterm 2 grade. Yeah. Right. And it is that the point values that I had said on Friday, where the one in Achieve, that is going to be 20 points. The metacognitive activity is going to be 10 points. So that'll be an additional 30 points, hopefully then boosting you 15% on top of whatever your score is. So theoretically, if you had like a 95% on the exam or 90% or whatever the high score was, you can now have like 105% or, whatever. So hopefully that'll boost you up. Okay. That was weird. Yeah, okay. Any other questions? All right, any questions at all about anything? Okay, cool. All right, so extra credit, due December 5th at 11:59 p.m. Eastern, which is our time zone. So I will also say, don't leave it till that last minute. Canvas has a tendency to freeze, especially on like reading day when it's trying to sync the entire university's like grades and everything, because usually that's a big day to like get everything processed right before finals. And so it has historically frozen right before it, in which case then you might not be able to submit. So don't bank on it being that really last minute. because it might not go through, in which case then it isn't turned in. So make sure that you do start it early because technical difficulties aren't going to be an excuse. So you have the 2.5 weeks or 3 weeks or whatever it is, and so you just want to make sure you do it promptly. Cool. All right. Let's talk about our alkynes. So our alkynes are essentially just going to be the same thing that we had with our alkenes, just you get 2 pi bonds. So we'll be able to do it twice for most of them. I'm going to highlight where it deviates. There will be a couple of reactions where we're going to get different products. So we just want to pay attention to those. But in general, it's going to be you just do it twice. Or if you only have one equivalent, then you just do it once. And we'll be able to control the number of times we do an addition reaction based on how many of our starting material we have, how many equivalents of the starting material. So quickly reviewing our alkynes in general, remember that the nomenclature is the exact same rules as everything else. It's just that our parent functional group is that YNE. And if you have an alkene and an alkyne present, you can have both of those parent functional groups at the same time. The ene comes before the ine because of the alphabet. There isn't a priority difference between your double bond and your triple bond. It is just alphabet for the parent functional groups. They're both considered equal in priority. So for that, you would just pick whichever one has the smallest number between them would be your numbering. And then if there's a tie, the alkene is the tiebreaker because of the alphabet. And so that's the big deal with the alkene. If we are naming this molecule, remember that our rings are always going to be our priority regardless of the number of carbons. So even if this had been a 3-membered ring, it doesn't matter. As of 2021, I think is when the rule changed, saying that the rings are always going to be the highest priority. So when we go to name this, our ring is our backbone. So that means our backbone is going to be that cyclobutane. So cyclo because it's a ring, but for the 4 carbons, ane because it's all single bonds between those carbons, right? So that is our backbone for that molecule. So when we go to name that substituent, we're going to have our 3 carbons. So we still have the same root of prop. But how we're going to designate the fact that there is an alkyne in it, I can't just say propyl, because propyl is the alkane. Propyl is saying I just have 3 carbons that are all single bonds. So my way of indicating that I have a triple bond there is to use that ine, the yn, in the middle of the YL. So it's prop is still for the 3 carbons. The ine is indicating the triple bond. The YL is telling me it's a substituent. And then I need to indicate where the alkyne is located. So because it's the only functional group there, I can put a 2 out front. So I can name this 2-propynyl cyclobutane. And to be even more clear, I can use that branch nomenclature. So I can use the parentheses to be like extremely explicit and make sure that like the number is always right next to what it's describing. So a more complete version would be having a 1, then the parentheses, 1 indicating that it's attached to the first carbon of the cyclobutane. Then I'd have a prop 2-ine-ol. And again, that E is just dropped because the Y is being counted as a vowel, and double vowels are hard to pronounce in the English language. If you include the E there, I would be fine with it. It would be just like a spelling thing. Achieve, I'm pretty sure, is picky about it, though. I don't think Achieve recognizes the E. And then just cyclobutane. Right. So the difference is just like with our alkenes, where we did enol, it's just that it's einol if you're trying to say that it's in that substituent. And then you just need to indicate where it's located. Cool. Any questions about naming the alkynes? Usually alkynes or unsaturations in the substituent is where things are like tricky for people. So that's why I wanted to highlight that example. All right. In chapter 13, we have, and actually pretty much everything since chapter 10, there are questions that still are starting to incorporate spectroscopy, because spectroscopy was chapter 10, and we didn't include that. So spectroscopy is saved just for Orgo 2 lab, so it is not a part of lecture, so it is not going to be an expectation that you would know it, so we're skipping anytime you get to it in the book or anywhere, you can just skip it. You will find in Achieve, I have included some spectroscopy questions, not in the homework, but like they're just extra ungraded assignments. So if you are in lab or you know you're going to be taking lab next semester or whatever, and you want to see practice problems that are, you know, ungraded, there are some in Achieve for you to do and have access to if you want to have that practice. It'll show you, you know, how it's relevant to the material you're learning right now. But for the sake of this class, we are skipping spectroscopy. But the bulk of our content is going to be talking about our synthesis of our alkynes and reactions with alkynes. That's where we're really going to focus. Before we get into those reactions, though, let's remember some fundamental things about our alkynes, their chemical and physical properties, just so that we have a quick little Gen Chem review, or chapter 1 and 2 review. So looking at our chemical and physical properties, so remember that it is nonpolar. So it has only nonpolar bonds, carbon, hydrogen, carbon-carbon bonds. Those are all nonpolar, so it is a nonpolar molecule. So the boiling point is going to be similar to our alkenes or alkanes, or it's similar between our alkenes and alkynes. So the boiling point is similar between all of our hydrocarbons because they're hydrocarbons. All they have are London dispersion forces. So they're going to be pretty similar. The places where they will differ is more so in surface area. So your alkynes are going to be able to stack better because they're linear. So you're going to have a little bit better surface area with your alkyne, so that can raise your boiling point if you're just looking at something like small molecules like propyne. That's going to have a higher boiling point because it's linear. It's going to have better stacking. We have the 180-degree bond angle. Our carbon atoms are sp hybridized. We get that 1 sigma and 2 pi within our triple bond. Because you always get 1 sigma and then you build pi on top of it. So the pi is coming from the 2 unhybridized p orbitals, meaning it's the 2 normal p orbitals. Those are what are making our pi bonds. So when we consider our orbitals, I drew out the orbitals for our triple bond here, specifically for acetylene, which is just our simplest alkyne. So for acetylene, in red, I did our sp hybridized orbitals. Those are on the x-axis, so those are linear. In the y-axis, in black, are those p orbitals, so those are what are making the pi bond straight up and down. And then the purple z-axis is the other set of p orbitals that are like straight out at you and going away from you. So they're all perpendicular to each other. And for the phasing, I just arbitrarily chose the top ones, the front ones, and then I elected to do the little orbitals, the little lobes of the orbitals. That way the hydrogens were still legible. So it is still, there's the back half, including the little lobe of our sp hybridized orbital. Right? Are there any questions about like orbital representations or anything that we're looking at there? Cool. All right, so just like with our alkenes, those pi bonds that are resulting are the ones that are farthest out, meaning that they're going to be the most reactive. So our pi bonds are going to be the parts that we're going to react with it, but we are going to need to keep in mind that the new thing about our alkynes is that this hydrogen is acidic. I'm going to say it's slightly acidic because its pKa is 25, which that's not particularly acidic because water is 14 and we said water is not that great of an acid. So propyne, or our terminal alkynes, our alkynes on the end have a hydrogen, they are going to be slightly acidic because if I have a strong base, one of my extremely strong bases, I'm going to be able to yank that off. So I'm going to need to keep in mind that when this is acting as a nucleophile, those pi bonds are the nucleophile. But my alkynes can also be acids, depending on the identity of the base that is present. Okay. And we're going to see that in play right now. So to make our alkynes, it happens via an elimination reaction. It happens via E2. Is how we do it. Because remember, E2 was the only reaction that worked on an sp2 hybridized carbon, right? sp2, sp1, and E1, they all required sp3. They couldn't be on a double bond. They couldn't work on like a triple bond, or, well, we didn't have to worry about triple bond, but it didn't work on a double bond. E2 does work on a double bond, which is good, because that's how we make our alkynes. So if I'm trying to go from this alkene to my alkyne, it's really hard to just yank off two hydrogens, right? Those are nonpolar bonds. So instead, what we need to do is to put leaving groups on our molecule and then do the elimination. So it's just going through an addition where we get two leaving groups so that we can make two pi bonds. Right? You get two leaving groups to make two pi bonds because every elimination reaction requires that leaving group and the beta hydrogen and a base. So this is what is known as vicinal, which is just saying that they are a 1,2 disubstituted, but on an alkane. And then the next one is vinyl. So we end up doing an E2 elimination to make our vinyl leaving group. And then we do the elimination again to get to the alkyne. So by just adding a base, if I have one equivalent of my base, I end up at the vinyl. And then, or you could think of it as if I have the vinyl and I add one equivalent of the base, that makes the alkyne. Or if I add excess of my base, then I can go directly from that vicinal product up to the alkyne. So I can go from having the two leaving groups all the way up to the alkyne directly, just by doing those two E2 eliminations. Which alkene addition did we do here? Do first with Br2? Do you remember what it was called? What elements are we adding? Bromine. What is bromine classified as? Halogen. Good, I'm glad you knew what the heck I meant by that. So it's a halogen, so which reaction are we doing? Halogenation, right? So the process of adding halogens, halogenation. Okay, which mechanism did our halogenation go through? Anti, good. That was one of our anti additions, or that onium ion, which I tried to emphasize by putting my bromines on opposite sides, right? Here, it actually doesn't matter because the one on the end is not a stereocenter. So I could just draw the conformational isomer, put bromine up here, but to try to reinforce in my brain that this is my anti-addition, I just by default put them on opposite sides so that I'm just like keeping that straight in my head, right? So that's one way to try to make sure that you're always remembering which mechanism it is if you do something like this, that even when stereochemistry isn't happening, to reinforce that you're like opposite sides, anti-addition, that's how I know my mechanism. All right, so that was adding Br2. What if I want to go from my vinyl bromide to this product? Which alkene, no, what? Yeah, which alkene addition do I need? Which reagent am I going to add? What element do you need? Br. What other element do I need? H. So which reagent do I need? HBr. And which mechanism does that go through? Carbocation. Remember, strong acid, carbocation. Right, so we can do that addition. That makes our geminal product. Geminal just means that it is a 1,1 disubstituted. So geminal is just saying that the two bromines are attached to the same carbon. Vicinal is not used as much, like that word isn't as common. Geminal is. So geminal, we're going to use it, usually abbreviated gets to just GEM, G-E-M. We'll use GEM to describe something that's disubstituted on the same carbon. So a geminal diol is where you have two alcohols on the same carbon. So this will be our geminal bromine, where you have, or geminal dibromine, where you get the two bromines attached to the same carbon. And then, again, I can just add base. One equivalent of base gets me back to my original alkene. So really, this is unnecessary. This was more so just point of discussion. And then if I add another equivalent of base, I can do another E2 elimination. Or if I had excess base, I could have gone directly. So whether it is that 1,2 or 1,1, as long as you have beta hydrogens, hydrogens on the opposite carbon or one away from where your leaving group is, then you can do those E2 eliminations, right? So that's the key thing, is we got to make sure that it is antiperiplanar. So when we look at our vinyl alkene, if I have, let's label these, I'll do HA and HB. Which hydrogen am I taking when I do that second elimination? Am I taking HA or HB? HB, because it must be antiperiplanar. It has to be the hydrogen that is on the opposite side of your leaving group. So HB is the one that we are taking. Don't forget everything that we knew about E2 still applies. Still has to be antiperiplanar or E2 does not happen, right? Must be antiperiplanar. Okay. When we do this elimination, if I'm doing this excess elimination from either my geminal or my vicinal, from either the 1,1 or the 1,2 disubstituted, if I have tert butoxide, then I only need 2 equivalents. I can have more, but I just need 2 equivalents in order to get to my alkyne. If I have sodamide, that sodium amide, so this gets read as sodamide. which is sodium amide. So it's Na plus NH2 minus. I need 3 equivalents. I need at least 3 equivalents in order to make that happen. Why is that? I heard something. Which one's the stronger base? O minus or N minus? N minus. Remember, less electronegative. They're in the same row, same period. Less electronegative is the stronger base. So that sodamide is my stronger base. So we got to think about what else could be happening. Acid base. So which proton am I taking? That terminal proton, right? The hydrogen on the end of the alkyne. So the difference in the equivalent is going to be, because that sodamide will also deprotonate our terminal alkynes, right? It's also going to be able to take that hydrogen. So O minus is not a strong enough base to take the terminal alkyne. So if you have sodium terbutoxide or potassium terbutoxide, you only need 2 equivalents because it won't deprotonate that end. If you have an extremely strong base, like that sodamide, that N minus, that is an extremely strong base. You can't stop the acid-base chemistry, right? Acid-base chemistry happens really quickly. So it's going to just immediately do that deprotonation. So the reason why you need a minimum of 3 equivalents is because I can't stop that. So if I only had 2 equivalents, I would get a mixture of products. I would have a mixture of my original starting material I would have my alkene, I would have my alkyne, and my alkyne anion. Because I would need one to go there, the second one to go there, but every time I use 2, a third one gets stolen to do that deprotonation. And I can't stop it, it just does it. So that means that now I have half as many to continue my process. So it means it'll eventually stall out and I won't be able to get it to react fully. So in order to get it to react fully, I need to have my 3 equivalent minimum. Because I can't stop the acid base. So in order to make sure that it actually all funnels into the alkyne product, I need to have 3 equivalents because I just got to let it do the acid base it's going to do anyway. Okay. Any questions about that? Does that make sense? That basically every time you use 2, 1 gets stolen, and so now you don't have as much to like keep making your alkyne. All right, so let's think about this then. What if I have this reaction? How many equivalents of sodamide do I need? What's the bare minimum that I need in order to make that alkyne? It's no longer 3. It's now 2. Why is it 2? What does this substrate not have that the other one did? Yeah. Say it again. Yeah, it's not a terminal alkyne. This is an internal, meaning it's on the inside. So this is an internal alkyne. So I don't have a hydrogen on the end, right? I have carbons on the end. So if I don't have that acidic proton to worry about, I don't have to worry about it, right? I can just use the two equivalents. So we just need to pay attention to our substrates and thinking about that acid-base behavior. Like, we just have to take that into consideration with our equivalency. All right, any questions about how we make our alkynes? It's just a normal E2 base comes in, takes the hydrogen, you make the pi bond, kick out leaving group. All right. If you make that alkynyl anion, so I get that negative charge. And remember, this base, we have to think about appropriate bases. So this base is going to be our strong bases. So this is like NaNH2, right? Or it could be N-butyllithium. N just means normal. Remember that we had that, so the N I said we don't normally use. The N just means straight chain, so it's just normal. It's a normal butyl group, a normal 4-carbon chain. Or you could have a Grignard. That's another really strong base, an ethyl Grignard. So that sp3 hybridized carbon. So those sp3 N minus or C minus, that's the bases that we need. These are extremely strong bases. So if you're trying to deprotonate it, you can't just use hydroxide. Hydroxide doesn't work. Hydroxide is a strong base, but I need an extremely strong base, right? So I need that sp3 hybridized N minus or C minus. That's going to deprotonate my alkyne. Once I get to that alkynyl anion, that is now a nucleophile. So I have, C minus, that's a good nucleophile as well. Could also be a base, right? Because I had to use an extremely strong base to get there. So this is also a base. So this is a base or a nucleophile. Most commonly, you're going to see it acting as a nucleophile, but it could be a base. So when we're using it as a nucleophile, if I imagine, I'm going to number this 1, 2. And for this top one, I'm going to say this is 3, 4, 5. What reaction am I going to do with these starting materials? If I have a strong nucleophile and a primary leaving group, SN2. So I see that primary leaving group. So I'm going to be able to do, there's my R, my carbon-carbon triple bond. Because I'm not using the pi bond, I'm using the anion on the end as the nucleophile. So there's my 1, 2, and then I continue out, 3, 4, 5. So I can do that SN2 reaction. What if I add an epoxide as my electrophile? What reaction am I going to be doing? What are my options? What do we do with our epoxides? We broke them open, right? Like the epoxides, they're highly strained. They want to pop open. So it's going to be a substitution reaction. So we're either doing SN2 or that SN1 type reaction. So then how did I know when I was doing SN2 or the SN1 type? If it was acid or base, right? So which one had the base or the strong nucleophile? SN2. So it's still just a normal SN2 reaction. And we're going to be attacking the less substituted side because that's what SN2 prefers. So it's just a normal SN2 reaction. So we get R, our alkyne again. And then you get there's carbon 3, there's carbon 4. Off of 3, you would just have 4 because we're going to pop it open that way. So then off of 4, I'm going to end up with an alcohol and my R prime. The alcohol is coming from the second step. That water is just protonating. So the reason you would want to do a water workup as opposed to an acid workup is because our strong acids are going to be able to react with the pi bonds. So you would just use a water workup to do that protonation and not have to risk reacting with your alkyne. So that workup is just protonating our alkoxide. All right, what do you think is going to happen in the last one? What type of reaction? Addition, yeah. I have that pi bond. Remember when we had Grignard? This is just a carbon nucleophile. So when we had like MeMgBr, we added the methyl in. We're going to do the exact same thing. We're just going to add that carbon in. So we're going to end up with our alcohol. So this is our addition reaction. We're adding that alkyne in. My linear bond angles got a little wonky there. Actually, all my bond angles are a little wonky. Let's try and make that a little prettier. Also, just a quick reminder, if you want to include the carbons, you can. But for our line diagrams, it's also okay just to show the line going through. I like to still leave a little break in there to reinforce where my single bond, triple bond, and single bond are starting and ending. But technically, you could draw the line all the way through and then draw the triple bond, and that's still saying the same thing. Okay, so the alkyne, as the anion, can still be just a normal nucleophile. Treat it like a Grignard, right? It's essentially just the same thing as our Grignards. Yeah. So the second one was SN2 because this is a strong nucleophile. So then our epoxide is the electrophile. So if I'm in strong base, strong nucleophile, it's going to just directly attack that carbon and kick out what is essentially the leaving group, but it is a ring opening. So because it's happening all in one step and is on the less substituted side, it is just a normal SN2 reaction. All right. What if our pi bond is the nucleophile? What's going on there? So if our pi bond is now our nucleophile, We're just going to do normal alkene style additions, right? So if I do that hydrogenation, if I had my alkene and I gave you H2 and palladium on carbon, what was my product? What elements am I adding? Hydrogen. So if I add hydrogen across this, what do I end up with? An alkane, right? If there's no pi bond anymore, it's just all carbon and hydrogen. It's just an alkane. Our alkynes are going to do the same thing. It is still a normal syn addition, just as we talked about before. But when you do that first addition to make your alkene, this is still reactive. This is not isolated. Because remember that alkene is reactive under these conditions. So if I have the alkene made, it just reacts again. And it'll do the hydrogenation again so that you end up with, I've added a total net of 4 hydrogen atoms across, which is just a normal alkane. This hydrogen is always in excess. It is not possible to limit that equivalency. So trying to limit the equivalency of a gas is extremely difficult, pretty much impossible. So it is very, very hard to try to limit the equivalency of a gas. So in that case, it is always in excess. So this H2 cannot be written as just like one equivalent. It doesn't work. If you have your alkyne with H2 palladium on carbon, you get an alkane. That's your only option. It goes directly from here to there. That is the product that you see. If you want to stop, if you want that syn addition, we need to add something that'll weaken our palladium. I need to add a poison, right? Just like how PCC, how we added that pyridine to poison the chromium so it didn't react the whole way up to a carboxylic acid. We're gonna do the same thing with our palladium. We're gonna add a poison, and our poison is going to be quinoline. This combination of reagents, which you do need to know the combination of reagents for Lindlar's catalyst, is going to stop at the syn addition. So it is poisoned, so it stops at the alkene. It is not going to be able to reduce the alkene. It will make my cis alkene because it is still a syn addition. So I'm still getting the hydrogens on the same side. So it's going to make my cis alkene. So if you do Lindlar's catalyst, having that quinoline, which is that lead calcium carbonate, palladium with the calcium carbonate, and then lead acetate and quinoline is the full combination of things. The quinoline is what is helping poison it. Lead also plays into it, but if you think about it as like that N, just like how it was pyridine, it's like pyridine, but it has extra benzene attached to it. So if you can remember that nitrogen is the poison, that can help you remember that that's where it's stopping. If you want the trans alkene, then we can't do a syn addition. right? If I want a trans-alkene, I can't have my hydrogens on the same side. I need them on opposite sides. I don't have an anti-addition that is going to add hydrogen atoms. So instead, we're going to do a radical reaction. So this is leading to the trans-alkene. And it is using either sodium metal or lithium metal and liquid ammonia. Note that this is not NaNH2. A lot of students will get tripped up on that because they'll see Na and they'll see NH2 and they're thinking it's the same thing. This is not the same thing. This is sodium metal, Na neutral metal, and NH3 as a separate molecule. So it's not ionic, it is two separate molecules, compounds, elements, whatever. Elemental sodium and then the molecule ammonia. This is a radical mechanism. So for our radical mechanisms, the important thing to remember is it's going to be that like fish hook. So it is that single-headed half arrow. So single-headed, meaning you only have it on one side of the arrow. Half arrow is saying that I only have one side labeled. That indicates the flow of one electron. There are two ways to show this initial radical reaction. So sodium, remember sodium has one valence electron. So it's in group 1, the first column, it has one valence electron. It just needs to lose that one electron in order to get the noble gas configuration. So it readily just like kicks out an electron, so it can become Na+, so it can be stable. So this sodium, you can either show it where you have the sodium is forming a bond with the alkyne. So I show that the one electron is coming out, and then one electron from the pi bond is coming with it, and then the other electron is going the other way. So the big thing here is that you just have to indicate where every single electron is going. So I'm showing that these two come together to make the bond. So when the arrows point at each other, that's what makes the bond. So I'm showing that I'm making a bond here between one electron from my pi and the one electron from the sodium. And then the other electron of that pi bond is just going to the carbon. So that's a kind of normal way to show that first step. Like this is our classic radical arrows. These will be the arrows when we get to our last lecture, when we show all of our radical reactions. We'll be using these same arrows. Another way to show it is to do what's known as a single electron transfer. The more classical, or not classical, newer way to show it. I mean, both of these are single electron transfers, but the newer way to show a single electron transfer is that this electron is coming in, and basically this is just showing sodium is just giving up that electron. Sodium is just, here you go, carbon, take it. And it just hands it off. And then because I'm increasing the electron density on that carbon, I'm going to have a repulsion so that the pi bond is going to break, and I'm going to give the two electrons to the other carbon. So what this is doing, and whichever arrows you prefer are fine. There's no any studies to indicate which one's better. So whichever one you prefer is totally cool. But what you end up with is going to be this radical anion. So the most stable form of this radical anion is going to be where our big groups are as far apart as possible. That's why we're getting our trans product, is because when I have all of this electron density, I'm trying to get everything as far apart as possible to be as stable as possible. So this is why we end up with our trans alkene, is because of this step. And then I have Na+. So these are exactly the same thing, right? They're just flipped over like a pancake. So these are exactly the same. So whichever one you want to draw, totally perfect. Whichever arrows are making you happier. So the next step is just acid-base. So this vinyl anion, the negative charge on the double bond, highly reactive, is going to react with that ammonia. Come on. And it's going to take that proton of the ammonia. So we're going to have our curved arrows start at the lone pair, go to the hydrogen of the ammonia, and then we give our electrons to that nitrogen. Please let me draw. Nope, okay. There we go. There we go. So we can do that acid-base. That protonates that anion. So then I just get a radical, which then another equivalent of sodium just is like, here, take another electron, become another strong base to do acid-base again. So it's 2 single electron transfers and then just 2 acid-base reactions. But that's what's actually giving us that product. So I'll keep our hydrogens in. Cool. All right. So next class, we'll get into the rest of our normal addition reactions using all the reagents from last week, but now with an alkyne. Right? So have a wonderful day.